Hey, it's me back again. My puffy coat on. Still kind of cold in here. Soft and puffy. Alright, let's do these physics problems. Probably going to take us a little while to get through all these. So, get comfy. Questions 1 through 3. And I talked about physics AP test stuff a little bit at the beginning of the 2012 video. So if you're watching this one first, you might want to go and just check that out real quick. All right, let's go. An object of mass 10 kilograms starts from rest at time t equals 0 and moves in a straight line for times greater than 0. The object's velocity v as a function of time is this. Oh, here I feel easy calculus coming on here, where v is in meters per second, t is seconds. How far does the object travel during the first 10 seconds? So if you want to know how far from velocity, that's an integral. The first 10 seconds, 0 to 10. This gives us displacement, right? Oh, we got to make sure there's no turnarounds in there, and there aren't. How did I check that so quick? Because just look at that, and let's factor the t out. 2 plus 3t. So that's going to be a negative time and 0. So there's no turnarounds in the greater than 0. So just make sure of that real quick. Because how far means distance. So let's see. The antiderivative of 2t is t squared. Antiderivative of that is t cubed from 0 to 10. So that's 1,100. Right. What is the instantaneous net force that acts? Okay, so I can get at force through acceleration. So acceleration is the derivative of velocity, which is 2 plus 6t. And then force is equal to mass times acceleration, net force that is, which is what we're looking for. So the mass is 10. So 10 times that. And at time 2 seconds, that's 120, 140. Is good. How much work is done by the net force between time 0 and time 1? It's a variable force, so you can do work is equal to the integral of force with respect to position. So this is going to be trouble for us because this is a t here. It's not the right variable. This needs to be position. So that's not going to do it for us here. But I also know that work is equal to the change in kinetic energy. So I think I can do this because I know what the velocity is. So I have 1/2, change in kinetic energy is 1/2 mv final, which is the v time 1 squared minus 1/2 mv initial, which is the time 0 squared. So that's 1/2 m, which is 10, times v1, the velocity at time 1 is 5, and the velocity at time 0 is 0. So I got 5 times 25, which is 125. All right. A force F accelerates a system of 2 blocks on a horizontal frictionless surface. The acceleration is 4 meters per second squared. The force with which Y pushes on block X has the magnitude of... Okay, so we need the interblock force here, so let's make some force diagrams. First of all, what's the magnitude of this? That, of course, this force only just thinks it's pushing on 6 kilograms. So if the acceleration is 4, then that's 4, and the total mass here is 6. So this force right here is 24 newtons, right? So now I can do a net force. You can make the force diagram here for either block, but the easiest, well, they're both easy. I'll do them both real quick and just show you that you could have picked either block. So this is block X. You got, of course, force of gravity, about 20 newtons. Normal force is about 20 newtons, just that times 10. And we've got this force, which is 24 newtons, and then I have the force of y on x. And I don't know what that is. That's what I want to know, which is y pushes on block x. So, well, the net force, sum of all forces, is equal to mass times acceleration for this particular block. So here, that's for F minus Fy on x. And the that force is 24 minus the thing I'm looking for is equal to the mass of this block 2 times the acceleration of the blocks, which is 4. So moving stuff around, that's going to be 16 newtons. You could have also, since this is a Newton's third law pair, force of y on x is equal to the force of x on y. And for this block, I've got 40 newtons of gravity, 40 newtons of normal force. If I make the equation for this, this is the only force. The force x on y is the only thing pushing on this. This one doesn't know about that, right? It just has this block pushing on it. So here, that force of x on y would be equal to the mass of this block times the acceleration, 4 times 4, which is also 16 newtons. They had to be the same because it's a Newton's third law pair. So either one would do. All right. Persons x, y. Oh, we had blocks x and y. Now we have persons x and y. And z walk along circular path of radius 50. Person x walks halfway around the path. Person y walks 3/4. I'm just going to start them all here. Magnitudes of their displacement vectors. So it doesn't say that they start in the same place, but it doesn't matter. So if x goes from here to here halfway around, their displacement vector is going to be like this. The person y goes 3/4 of the way around. Their displacement vector is going to look like this. And person z goes all the way around, walks completely around the path, which is the following magnitude. So the magnitude of the displacement vector for z is 0 because they're back at the same place. So least to greatest would go z is the smallest, then y, then x. Z, y, x. Right, what is this question about? Do you know the difference between displacement and distance traveled? That's what this question is about. I'll tell you what a smart test taker does. A smart test taker looks at the problem and tries to kind of see through the problem to the intention of the person who wrote the question. Oh, look at that. I did this in the wrong order. I did 1, 2, 3, and then 7. Sorry about that. Now I'm going back to 4. Oh well, you can handle that. So that's what that question's about. Do you know the difference between displacement and distance? A small particle starts from rest from the origin of an xy coordinate system and travels in the xy plane. Its acceleration in the x direction is this. Its acceleration in the y direction is this. What's the x coordinate of the particle when its y coordinate is 12? Okay, well, it starts from rest at the origin. Okay, so, and it's got constant acceleration in the y direction, which means these are the equations I can use for constant acceleration. So its y position, I can just substitute all these with y's. Its y position is equal to 1/2 times its acceleration in the y direction times t squared plus its initial velocity which is 0 times time, plus its starting position in the y direction, which is 0. So that means its y position is just 1/2 t squared. And if we want to know what's the x-coordinate of the particle when the y-coordinate is 12 meters, I need to know the time that goes with this. So when the y-coordinate is 12 meters, the time is going to be the square root of 24, about 5 seconds. Okay, now the x-coordinate here in the x direction, it's going to do the same thing. We move down here. In the x direction, its position is 1/2 a t squared plus initial velocity times time. It's starting from rest, so that means its initial velocity in both the x and the y direction is 0. And it's starting at the origin. So those are gone. And its x position would just be equal to 24 meters. Those cancel out, plug in time 24, and there you go. If the speed of an object moving in a straight line is increasing at a constant rate, then the net force acting on the object is... Okay, so an object's moving in a straight line, and the speed is increasing at a constant rate. So that means the slope of the v versus t is constant, which means that it has constant acceleration. And if you have constant acceleration, you also have constant net force. So net force is 0, no, constant, but not 0, decreasing, increasing. So there you go. If your speed's changing at a constant rate, that means you have constant acceleration, and that means constant net force. All right. The toy raft, so we're looking down on this. The toy raft shown in the view above is sliding due east on frictionless ice, sliding this way, at a constant speed v sub 0. When a fan blows on its sail, producing a constant acceleration to the north, which of the following could indicate the path of the raft while the fan is blowing? Well, it's going to keep its constant velocity in this direction because this acceleration only affects it this way. And that acceleration in this direction is going to cause the raft, if you only look at its y position, or its north-south axis position, that's going to increase steadily because there's a constant acceleration. So it's going to look like this. I guess this is the other possible answer that could be tempting, but this is moving at a constant velocity in the x direction and a constant velocity in the y direction if you're doing this. And this has non-zero acceleration, so the velocity in the y direction is not constant. So that's why it cannot be that. And I guess this is for maybe the person who thinks that, oh, as soon as the fan starts blowing, it's just going to go like that. But that is not how things work. It's like you remember broom ball, when the ball's rolling along like this and you want to get it to turn this corner. If you only tap on it this way, it goes like this and rolls into the vending machines over there, which you saw demonstrated by some Rockbridge County High School teachers. All right. Velocity v in meters per second of an object. Oh boy, I smell some easy calculus happening here. Moving in a straight line, given by this function of t, the total distance the object travels between time 1 and time 2. Does it turn around between time 1 and time 2? Let's see. Methinks the answer is no, but we need to just check. So I'm going to factor 2t out of that, which gives me 2t squared plus 1. That's equal to 0 at 0 and not equal to 0 ever here because this is always positive, so no turnarounds to worry about. which means I just have to do this. Didn't we just do this on the front page of this? Yeah, like number 1? Huh. Okay. Because they really, really want to know if we know how to do easy calculus. So this is from the same test. So antiderivative of this is t to the 4th plus t squared. I guess the other one, it had the 0 starting point, and this one has a 1. I'm just trying to, from the point of view of the person writing this test, like I don't think I would include both of these questions on the same test. But maybe it's because of this. I don't know. Plus t, so plus 4 minus 6. 20 minus 6 is, what did I do? Oh, 1 to the, sorry. Do you know what 1 to the 4th power is? I was plugging the 1 into that. That's what I did. That should be a 2. Sorry. All right. Collision. Collision makes me think. Momentum. Momentum. So in a collision, initial and final momentum are equal to each other. Or in other words, momentum is conserved. Object X, yada, yada, yada. This stuff here. So is this, which of the following is true of the collision? It's elastic because momentum is conserved. That's not how we know whether a collision is elastic or not. Elastic collisions are happen when kinetic energy is conserved. So is the kinetic energy conserved here? Well, yeah, sure. 1/2 mv squared, 1/2 mv squared. It's all the same numbers here. They just switch. So it is elastic because kinetic energy is conserved. That's looking good. It is inelastic because momentum is not conserved. Of course, the momentum is conserved. It's just 5m before. That's a total mv and 5m there. It's inelastic because kinetic energy is not conserved. Kinetic energy is conserved. The total 1/2 mv squared, 1/2 mv squared. It's the same. They're both. More information is needed. Oh boy. You can be really confident to pick that one. So more information is needed by me to determine whether the collision is elastic or inelastic because I forgot. How about that? Then you can pick that one. So the answer is B. 20 kilogram box moving at an initial speed of 10 meters per second slides 25 meters to the right on a horizontal floor before it comes to a complete stop. What's the coefficient of friction between the box and the floor? All right. It's initially moving at 10 meters per second. It comes to a stop. So there's a couple of things we could do here. Let's see. I guess I'll do them both for you real quick. So one would be kinematics. Friction force is constant. So if we start with an initial velocity of 10 and we come to rest in 25 meters, then what's the acceleration? So Vf squared equals Vi squared. Is this equation on the equation sheet? We didn't see it on the last one, or we didn't need to use it. Sure. It is with the, right? That's your V, that's like your Vf squared. It looks slightly different, so we need to be familiar with this. The Vx sub 0, they had a hard time making that 0 sub. So that's like your Vf squared, that's like your Vi squared to a delta x. All right, so that's 0 is equal to 10 squared, that's 100, plus 2 times delta s, that's 50 So the acceleration is -2. Makes sense that it would come out to be negative here. And that means that the friction force is the only thing acting on this, so that friction force is equal to mass times acceleration. So that's going to be -40, or 40 in magnitude. And friction force is equal to mu times normal force. So that friction force 40 is equal to mu times the normal force is just 10 times this because it's not on a ramp. So that looks like 40, or that's 0.2. Right. The other way to do this would be to say, hey, the work done by friction is the thing that's changing the kinetic energy, right, down to 0. So the work done by friction is equal to the friction force, which is mu times the normal force, mu mg, times the distance, which is, 25 meters, not 10. And that's equal to 1/2 mv final minus mv initial. Mv, and this is the work done by friction is going to be negative work, right? Because it's tapping energy out of the system. And then this will be 1/2 mv squared final, which is 0 because it's coming to rest, minus 1/2 m final, or the initial velocity, which is 10 squared. So those cancel out, and I get mu is equal to, the minus signs cancel out. This is 250, and that's 50. So 0.2 that way also. Those are your two options there. 23, block of mass m is pulled across a rough horizontal surface. I feel like we saw this real close to this. Just maybe being asked for a different thing. Angle's called theta instead of phi this time, to horizontal, the coefficient of kinetic friction. So this time they want the coefficient of friction. So, make me do it again? Nah. Let's see. I'm going to rummage through these papers here. It's the same force diagram, and the same. Okay, so what do we want this time? This time we want the coefficient of friction. So I think this time what we want to do is set this equal to this, right? So if I want to know what that coefficient is, mu, my coefficient, times the normal force, which is mg minus f sine theta in this case. Mu times normal force is equal to f cosine theta. So mu is equal to f cosine theta over this. Yeah. This is just like a situation you want to be familiar with, right? It comes up at an angle theta. All right. Or 24. This sure is an easy problem if you don't overthink it. So just looking at, never mind what's going on up here. Here you've got this thing, and you've got 1, 2, 3, 4 little stringies pulling up on it. So each one of those must be supporting a quarter of the weight. They're each W over 4. It cannot be otherwise. If you're thinking to yourself, well, I can see how they'd have to all add up to W, but why do they all have to be equal? If they were not equal, then that would cause these, if you had more on one side than the other of one of these pulleys, that would cause those to rotate. And this is not rotating. It's at rest. So they got to be all equal. And you can't have more tension in one end of a string than the other. So that means here, that's W over 4, just like it is at the other end, and so is that. So if this pulley has two of those W over 4s pulling on it like this, then the spring scale is going to read W over 2, because there's two of them. In an experiment, an object is released from rest from the top of a building. Its speed v is measured as it reaches a point that is a distance d from the point of release. If this distance was doubled, then what would be the new speed? So we need velocity as a function of distance, and then this is one of those like proportional reasoning problems, right? So let's think about which one of these gives us velocity as a function of distance. Velocity as a function of time, position as a function of time, and this is like velocity here, and this is like as a function of distance. So okay, that's going to work. So what we're really looking at here is this kinematics equation. If you just say d is like the distance that it's covered, then I can tie it to these variables. It's released from rest, so that goes away. So that means my velocity at time t is equal to 2 times the acceleration times how far it's fallen. So if the distance was, and if you want to solve this for v, so that means v is directly proportional to d to the 1/2 power. So if you double the distance, if you put a 2 under here, that's going to increase it, but only by the square root of 2, because that doubling is underneath the square root sign. Right? You think you're going to see more of those proportional reasoning questions? Oh yeah. The relationship between the magnitude of the restoring force F and the resultant displacement x from equilibrium for a nonlinear spring, so that means no force equals kx, is given by the equation F equals kx squared. And they say magnitude here, so if we were paying attention to directions, it would really be F equals negative kx squared, but they're just talking about the magnitude. What's the potential energy of the spring when it has been compressed a distance of x sub 0? So this is just the same. We saw this problem in a slightly different form. If you have your force equals negative kx, then that gives you spring potential here. You ditch the negative sign, take the antiderivative. So if it's negative kx squared. Why am I putting the negative sign in here? Because it would be there. They just said magnitude here. So whatever. These are all positive. You can't make that mistake. So then it would be the antiderivative of this, which is 1/3 kx cubed. All right, two blocks of masses m and 2m are on a frictionless horizontal surface as shown above and are held in place with a compressed spring of negligible mass between them. If the blocks are then released and the block of mass 2m leaves the spring with a velocity of v, the velocity of the center of mass of the blocks is, well, how do I know it's that? Because they're both at rest to start. Even though there's a spring in between, they're pushing off each other. This is like an equal and opposite situation with the spring being sort of like a Newton's third law intermediary, or like middleman or middlewoman, or whatever. In other words, the spring can't push harder on this block than it pushes on this block. There's only one spring force here, right? The two ends of just like you can't have different tensions in the two ends of a string, you can't have a different amount of force at the two ends of this spring. So if that's true, well, the spring is also pushing on them for an equal amount of time. And if that's true, that means the force times time on this is equal to the force times time on that, which means the impulses are equal, which means the change in momentum are equal, which means the total change in momentum is 0. And if the total change in momentum is 0, why does that mean the velocity of the center of mass is 0? Well, remember how to find the center of mass? Like this. So what if the things are moving? Well, then the center of mass would be moving, and these would be changing, right? Of course, the masses would be the same. So what if you took the time derivative of this? Oh, sorry, and this is all divided by, let me bring this out to the front, all divided by the total mass. But that's just a constant, right? So if I took the derivative of this, the time derivative, the derivative of x is v, so that would give me the velocity of the center of mass, would be equal to the derivative of x1 with respect to time would be v1, and that's just a constant. And that is, this would be the velocity of the center of mass. But look at this. What is this expression? That's the mv for each one of the particles. That's the total momentum. And you know what happens with the total momentum in a collision or an explosion like this? It's conserved. So the velocity of the center of mass stays constant because momentum is conserved. So I don't know, maybe that's a little tricky. Uh, 60-gram tennis ball moving at 15 meters per second strikes tennis racket and rebounds 10 meters per second in the opposite direction as shown above. Ball is in contact with the racket for this amount of time. What's the magnitude of the average force? So impulse is equal to change in momentum. If you're talking about force and time, you got to be thinking about impulse and change in momentum. So the impulse is equal to average force times time, and then delta p. We just have to be very careful here about signs. So let's say that this is the positive direction, then this is positive, and this is negative. Okay? So then average force, that's what we're looking for, is equal to m times you could write it like this, right? Your change in momentum, mv final minus mv initial. So there's a m, and then I have my final velocity is negative 10 minus my initial velocity is positive 15 divided by 0.03. 0.06 over 0.03 is 2, so 2 times negative 25 is negative 50. They say, what is the magnitude? So that would be that. How does the magnitude of the average force exerted by the ball on the racket compare to the magnitude of the average force exerted by the racket on the ball? It's equal. Newton's third law. There's only one racket-ball interaction, so it's not possible for that to be like a greater amount of force for one than for the other, because it's the same force. There's only one interaction. The racket and the ball are interacting with each other. There's only one interaction, so they have to be equal. That is Newton's third law, jumping up and smacking you in the face right there. All right, and then there was one free response question from this year where we knew everything we needed to know to be able to do it. The free response questions tend to kind of, not always, but sometimes they kind of ramble through different topics and some of those we don't have yet, so that's all. They like to do rotation stuff in the free response questions also, and that is coming soon, but not under our collective belt yet. So what do we have here? 0.3 kilogram cart moving at 2 meters per second to the right collides with, okay, so as soon as I see that, I'm already thinking probably there's this momentum kind of thing happening here, with this cart initial moving at this to the left, okay, to the right, to the left. Be careful with the signs. So I'm going to say right now, so I don't lose track of this, I'm going to make to the right positive. So this is positive, and this is negative. Okay. After the collision, the second cart moves to the right with the speed of this. So that's to the right. That's positive. Assume friction is negligible. Calculate the magnitude and direction of the velocity of the second cart after the collision. Okay, I'm going to express my physics thoughts completely and clearly. Momentum is conserved. I'm even going to write some words. So that means the initial momentum and the final momentum have to be equal. You could, I think that that's fine to just write that. If you wanted to make a stronger indication that it's the total momentum, you could do this. That's fine. I think that that's optional. It's the next step that's important that you articulate here in the initial condition. I have, I'm going to say m1 times its initial velocity plus m2 times its initial velocity equal to m1 times final velocity plus m2 times final velocity. So let's see. Let's jam all this stuff in here. So 0.3 times the initial velocity is positive 2 for that. Cart 2 is 0.1. Its initial velocity is negative 3. Mass 1, its final velocity is I don't know what. That's what we're looking for. And cart 2 moves to the right with a velocity of that. All right, so just need to solve for that. Where's my calculator? There's a calculator. So let's see. So that's 0.3 times 2 is 0.6 minus 0.3. Sorry, that's embarrassing that I'm doing that with a calculator. And then minus 0.12. And then I'm going to divide that by 0.3, which looks like that's going to be 0.6. That's positive. Now, I decided that positive meant to the right, but that's my decision for me doing my work. So I need to say that it's 0.6 meters per second to the right. I need to bring that back around to what actually does that mean that it's positive, right? That's important. That's probably, we'll look at the scoring guide in a minute, but that's probably worth a point there. Is this an elastic collision? Well, it's an elastic collision if kinetic energy is conserved. So let's just find the kinetic energy. The initial kinetic energy is 1/2 m1 v initial squared plus 1/2 m2 v initial squared, 1/2 times m v squared plus 1/2 m v squared. You can put the negative in there, but it doesn't matter because it's going to get squared off. And then the final would be 1/2 m1 v final squared plus 1/2 m2 v final squared. And I have that stuff here. That's 1/2 is 0.3 times 0.6 squared plus 1/2 0.1 times 1.2 squared. All right, let's find those. What do you think? Got a guess? You probably already did it. I haven't done this one before, believe it or not. Or at least I don't remember. That's very possible. But I have done it. I think that if they're going to bother with this, I think they might try to make it work. Let's see. Drum roll, please. Nope. Not even close. Not even close. So the answer is no. And you could talk about exactly what happened, but all you have to say is that the kinetic energy is not conserved. All right. What now? So now we're going to remove this cart. This one continues to move to the right and then collides with and compresses an ideal spring. So that means I can use Hooke's law, and spring energy is 1/2 kx squared. That's what that enables. Whose right end is attached to a fixed wall. Okay, so this is this little cart. It's coming in here, and this is the classic banging into the wall like this. Calculate the potential energy of the spring when it reaches maximum compression. Okay, so how much? So what do we have here? We're going to have a 1/2. Sorry, let me back up one level here. We're going to have the kinetic energy of the cart is going to turn into the stored energy of the spring. Right? Yes. Give me 1 sec here, folks. Hold on. All right, sorry for that pause there. So kinetic energy of the cart is going to transfer to the stored energy in this spring. So that oh, and I guess we're not doing this yet. We just need to find what that's equal to. So we just need to do this. So that 1/2 mass of the cart times its velocity, which we know that it has a speed of 1.2 meters per second. That gives us about 0.216 joules. And here, maximum compression of the spring is this. So now we're going to use the fact that it's an ideal spring, so its stored energy is 1/2 kx squared. That was a long bell. I think that means that school's out for summer. So we'll solve that for k. It's about 43 newtons per meter. And last part, suppose instead that the spring is nonlinear and that we have this instead. Calculate the value of B if the spring is compressed this much. So this, we need to remember that our potential energy function is the antiderivative of this, and ditch the negative sign. So here, that potential energy function is going to be 1/4 bx to the 4th. And we have the same amount of energy, so 0.216 now is equal to 1/4 b times the same compression to the 4th. So that constant b will be equal to, let's see, $8,640. What would the units for that be? So probably that's easiest to get at. I wonder if they would have a point associated with that. We're going to put them in there just to be safe. Force is equal to negative bx cubed, so the b is units of force over units of distance cubed. So that would be newtons per meter cubed. All right, I got the scoring guidelines here. Let's see how we did. And you can see how they distributed the points and what they thought was important. So first one, you want a correct statement of conservation of momentum. That could be the equation. Say momentum is conserved. I don't know if they would count that as that statement or not. So that's where the 1 point is, not for this. For correctly substituting, which we did, for a correct answer with units, which we have, and for correctly indicating that the direction's to the right. So we had to say that. That got a point. So we're all good there. We got 4 out of 4. For part B, we got the same things that they did. And no, collision is not elastic. And what our examples, final kinetic energy is less than, it's not conserved. So what we said is fine there for answering no. So you didn't actually have to have the right numbers for this. You just had to say no. Those are those 2 points. For part C, for a correct statement of the conservation of energy, which we have, and 1/2 times, uh-oh, that doesn't look like the answer that I got, though, because no removed. What did we do wrong there? page to look at. Oh, I did the mass of the wrong cart here. That's going to mess up some other things here. So that should be 0.072 joules, a third of that. And let's see, so let's just pretend that we did use the right mass. Then just looking at what they gave points for. Statement of conservation of energy, which we had, for correctly substituting, which I didn't do. I messed that up. And then for correct answer with units. So that's the correct answer. If we're keeping score, I would have got 1 out of 3 on that. And then for part D, they want a correct expression for the potential energy of a spring. Got it. Good point. Substituting into the above equation. Got it. And we would get this point, even though we got the wrong answer for this previous part. If you correctly substitute that later on, this is like when I write on your test, okay, fix, that's that kind of situation. For corrections, we want to fix it, but you wouldn't get double penalized for making that one mistake. And that's going to change that. And then the last part, oh, if the wrong cart was used in part C, then it's at the line. Well, I didn't exactly use the wrong cart. I kind of swapped there, mixed and matched. I wonder if they would have given that to me. They would give us those points for sure, though, because we didn't make a new mistake. Setting up the correct integral, we did that. Correct equation, we did that. And we did this, but we substituted the wrong thing again, so that answer now is going to be 2880. And look at that. Correct sign, so they need you to get rid of the negative sign here, just like you can't have a negative spring constant in newtons per meter. This B would be positive, and they did want the units. And that had a point. Correct sign in units. All right, there you go.